So since 2017, the AI industry has basically spent, you know, billions of dollars and millions of gigabytes of VRAM memorizing a piece of data that mathematically we don't even need.
Yeah, it's actually kind of crazy to think about.
Right. So welcome to AI Paper Slop, the YouTube series, where we try to extract the signal from the noise for technical folks. And today we are looking at a paper that proves standard transformers have been wasting up to half of your inference memory.
Literally half.
Exactly. It's a paper from BrainChip Inc. It was published at ICML 2026, and it's called Do Transformers Need 3 Projections? Systematic Study of QKV Variants. And I just want to give you the absolute bottom line right up front.
Yeah, get right to it.
So standard attention uses separate query, key, and value matrices. But this paper proves you really only need 2. By keeping the queries separate, oh, absolutely. And it stacks flawlessly with head sharing techniques, like grouped query attention for up to a 98.5% cache reduction. And all of this for a completely negligible 2 to 3% drop in perplexity at the 1.2 billion parameter scale. I mean, if you're an ML engineer fighting VRAM limits, this is just a massive immediate win.
Oh, totally. It fundamentally rewrites the rules for autoregressive generation, honestly. We're looking at a structural change that, essentially doubles your context window overnight. And that's using the exact same hardware budget you are running right now.
Yeah, and the fact that we are 8 years out from the original attention is all you need paper makes this wild to me. Like, the standard QKV structure query key value has been treated as absolute untouchable dogma.
Right, nobody questioned it.
Exactly. So why did the authors of this paper suddenly suspect that this redundancy even existed in the first place?
Well, it really comes down to looking at the broader architectural landscape outside of pure transformers. So if you look at standard self-attention, it has a projection complexity of 3 ND squared.
Okay, and what does that actually mean for the hardware?
Well, what that actually means in practice is that you're multiplying your input token by 3 completely distinct massive weight matrices just to create 3 separate representations.
Right, super heavy.
Exactly. But if you look at contemporary architectures, like, say, modern state space models like Mamba, or even traditional convolutional neural networks, they use much more unified internal representations.
Oh, yeah, they don't split everything up.
Right. They don't split a single token into 3 distinct parallel vectors just to process it. But transformers have stubbornly maintained this tripartite redundancy. So the BrainChip researchers basically just asked, well, what happens if we force these learned projections to share weights?
Okay, but just to make sure we are totally aligned on the terminology here for anyone listening, when we say sharing, we really need to differentiate this from what people are already doing with their models. Like you mentioned grouped query attention earlier. How is projection sharing different from the head sharing we already use?
Yeah, that is a critical distinction. So head sharing like group query attention, or GQA, that reduces the actual number of attention heads.
Right.
For instance, multiple query heads might share a single key and value head. But inside those heads, the key and the value are still produced by completely separate mathematical projections.
Oh, I see.
Yeah, this paper is proposing projection matrix sharing. They are reducing the matrices themselves.
Got it. I always visualize standard attention like an office filing system.
Oh, that's a good way to look at it.
Yeah, like the query is the search term you type into the computer. The key is the label written on the physical folder. And the value is the actual document inside that folder. So for almost a decade, we've built these systems assuming that the label on the folder and the document inside absolutely must be processed by completely different neural networks. And this paper is just asking, hey, can the label and the document just be the exact same thing?
Yeah, and that analogy holds up perfectly when we look at how the researchers tested this, because they didn't just guess, they ran a really systematic evaluation.
Right, they brought the receipts?
They did. They trained models across synthetic reasoning tasks, computer vision benchmarks, and causal language modeling. For the language modeling, they trained 300 million and 1.2 billion parameter GPT-style models.
And that was on what, the Slim Pajama data set?
Yeah, exactly, on 10 billion tokens from Slim Pajama. And they tested 3 specific constraints. First, Q equals K equals V, where everything is one single projection.
Okay.
Then Q equals K minus V, where the query and key share a projection. And finally, Q minus K equals V, where the key and value share a projection.
All right, so let's talk about the empirical results. Because in the paper, it's basically a bloodbath for some of these variants. Let's start with the most extreme version. Q equals K equals V. So single projection matrix for the search term, the folder label, in the document.
Yeah, that was a complete catastrophic failure for language modeling.
Oh, wow. How bad was it?
Well, at the 300 million parameter scale, forcing all three to share a single projection resulted in a 25.4% degradation in perplexity.
Ouch.
Yeah. And perplexity is essentially our measure of how confused the model is when predicting the next word. So a 25.4% drop means the model became significantly worse at just understanding language.
Because it's just too constrained, right?
Exactly. Language requires complex causal routing. A single monolithic representation, it just doesn't have the mathematical capacity to handle addressing, matching, and content delivery all at the exact same time.
Okay, so the extreme constraint is just dead on arrival. But the next variant, Q equals K minus V, where we share the query and the key, but we keep the values separate, that actually looks like a trap to me.
It really is a trap.
Yeah, because if I remember the charts correctly, the training loss didn't look completely disastrous at first glance.
No, it didn't. The Q equals K minus V variant yielded a relatively modest 4.9% degradation in perplexity compared to the baseline. But if you implement this for causal language modeling, you run headfirst into a fatal mathematical flaw.
Wait, what happens?
Well, when you set the query equal to the key, you compute the attention scores by taking the dot product of the key matrix with its own transpose. And mathematically, that guarantees a symmetric attention matrix.
Okay, I'm trying to visualize what a symmetric attention matrix actually does to the generation process.
Yeah.
Does that basically mean the model is looking backward and forward in the exact same way?
Yeah, think about the core task of causal language modeling. You are predicting the next word based strictly on the past words.
Right, you can't see the future.
Exactly. You cannot attend to the future because it hasn't been generated yet. But if your attention matrix is inherently symmetric, the relationship from token A to token B is forced to be mathematically identical to the relationship from token B to token A.
Oh, I see. So it fundamentally fights against a causal mask.
Right. It totally breaks the directional bias that language generation relies on.
Okay, so the math is fighting the causality. But, let's say I was stubborn. Let's say I just didn't care about the perplexity drop and I somehow hacked around the symmetry just because I was really desperate to save VRAM. If I unify the query and the key, how much cache am I actually saving during inference?
You save absolutely 0 megabytes.
Wait, 0? How is that even possible if I just combine two of the matrices?
Because of how autoregressive generation works physically on the GPU, like when you generate text, you spit out one token at a time. And to avoid recalculating the entire sequence from scratch every single step, which, would be agonizingly slow, we cache the keys and the values from the previous token.
Right, the KV cache.
Exactly. That is your KV cache, but you never cache the queries.
Oh.
Yeah, the query is just the current token looking for past information. So if your model uses Q equals K minus V, your keys and values are still completely separate tensors. You still have to cache both of them.
Wow. So you've degraded your model's performance, broken its directional bias, and you literally haven't saved a single byte of memory.
Yeah, it's pretty brutal.
That is a brutal trap. Which I guess brings us to the actual winner of the paper, right? Q minus K equals V.
Yep.
So the query remains an independent matrix, but the key and the value are unified into a single projection.
Right. And this is where the magic really happens. At the 300M scale, this variant only suffered a 3.1% degradation.
Okay, that's not bad.
And when they scaled the model up to 1.2 billion parameters, the gap actually closed even more. It dropped to only a 2.48% degradation compared to the standard unconstrained transformer.
That's negligible.
Basically, yeah. And most importantly, because the query and the key remain independent, the attention map preserves the asymmetry you need for causal routing. Token A looking at token B produces a completely different score than token B looking at token A.
Right, okay, but I have to push back on the mechanics of this, though. Let's go back to my filing cabinet analogy.
Mm-hmm.
If the key and the value are mathematically the exact same tensor, how does the model not just output gibberish?
It's a fair question.
Like, the label in the folder is literally the document inside.
Mm-hmm.
Use a vector to find a vector, and then you just output that exact same vector. How is the neural network extracting any meaningful semantic data from that?
Well, it forces us to reconsider how much capacity these high-dimensional vectors actually have. Think of the projection vector, like a complex musical chord.
Okay, a chord.
Yeah. A chord has a frequency, but it also has amplitude and timbre. The frequency might tell the model where to route the information, so acting as the key, while the amplitude carries the semantic meaning, acting as the value.
Oh, that makes sense.
Right. The representational space of, say, a 4 by 96 dimensional vector is incredibly rich. When you impose this hard constraint during training, forcing the key to equal the value, the model simply learns to multiplex.
So it's double dipping into the same numbers.
Exactly. It learns a single shared projection that successfully packs both structural addressing and semantic payload into the exact same numerical space.
You know, it's almost like the model was previously being lazy. Like
Yeah.
we gave it two massive separate matrices, so it just used them, but it didn't strictly need them to hold that information.
It's funny you say that because the researchers actually proved that this laziness exists in standard models.
Wait, really? How?
They analyzed fully trained standard QKV transformers, so models trained without any of these constraints, and they measured the cosine similarity between the learned key and value matrices.
Okay, and for anyone listening, cosine similarity basically measures how closely two vectors point in the same direction in high-dimensional space, right?
Yes, exactly. And in a standard model, the key and value matrices naturally exhibit a high cosine similarity of 0.73.
Are you kidding? 0.73.
Nope. They already want to occupy similar representational spaces naturally.
Wait, so for the last 8 years, we have been burning massive amounts of cloud compute and GPU memory to learn a value matrix that is naturally 73% identical to the key matrix anyway.
Yeah. We basically have, by contrast, the query matrix maintains a much lower similarity to both. It's around 0.42 to the key and 0.31 to the value.
Because that asymmetry is actually useful.
Right. The asymmetry between the query and the KV pair is what actually matters for attention. The distinction between the key and the value is largely a vestigial artifact of just how we originally wrote the architecture in 2017.
Wow. Okay, so if the math works and the causality is preserved and the model isn't confused, the real question for anyone listening who actually deploys these models is, what does this actually do to my cloud bill? Like, how does this change the physical constraints on a GPU?
Well, during generation, the KV tash is your absolute primary bottleneck. It dictates how many concurrent users you can serve and how long your context window can be.
Right.
Because Q minus K equals V forces the key and value to be identical, you only store the key tensor in memory. When the attention mechanism needs the value to compute the output, it literally just reads the key tensor a second time.
So you instantly mathematically have your KV cache footprint.
Instantly, yes.
Let's put some specific numbers on that for the engineers listening right now. If you're trying to deploy a model with a 32K context window and a batch size of 32 using a standard QKV transformer, the paper notes you need 83.9 gigabytes of VRAM just to hold the KV cache.
Which means you are already out of memory on a standard 80 gigabyte A100 GPU, just from the cache alone.
Just the cache.
Yeah, and the model weights aren't even factored into that yet.
Right, so you'd normally have to shard that across multiple GPUs. But if you drop in the Q minus K equals V architecture, that exact same cache drops to 41.9 gigabytes. You immediately save 42 gigabytes of VRAM. You can fit that batch entirely on a single GPU.
The infrastructure cost savings are just staggering. The authors actually mapped out a production scenario serving 100 concurrent users on A100 GPUs with that exact 32K context window.
Okay, and what did that look like?
With a standard model that requires 7 GPUs, which runs about $14,000 a month in standard cloud compute. But with Q minus K equals V, your cache per user is halved. You can pack 30 users onto a single GPU instead of 15.
Wow.
So you only need 4 GPUs. Your cost drops to $8,000 a month. That is a 43% infrastructure cost reduction simply by changing a few lines of code in the model definition before training.
That's insane, and we haven't even stacked this with other optimizations yet. We mentioned group query attention earlier. GQA is basically the industry standard right now. Like Llama, Mistral, they all use it. GQA means 8 query heads share a single KV head.
Right. And because projection sharing operates inside the attention head, it is entirely orthogonal to head sharing.
They don't interfere with each other.
Exactly, they multiply. GQA8 alone reduces your cache by 75%. But if you apply the Q minus K equals V constraint inside those grouped heads, a configuration the authors call QGQA8, you have that remaining cache again. You achieve an 88% total cache reduction.
So if GQA is like, carpooling to save gas, Q minus K equals V is like making the car itself half the weight, and we can absolutely do both simultaneously.
Yeah, and you can take it even further to MQA, multi-query attention, where every single query shares one global KV head.
Oh, man.
If you use QMQA, so one single head, and inside that head, the key and value are unified, you hit a 96.9% cache reduction at the 300M scale. At the 1.2 billion scale, it hits a 98.5% reduction.
That is just ridiculous.
Your memory footprint practically vanishes, and the model still only takes about a 3 to 4% perplexity hit.
To put that 98.5% reduction into perspective for you, that 1.2 billion parameter model at a 32K context length goes from requiring 5.9 gigabytes of cache per user down to 88 megabytes.
It's just wild.
88 megabytes. You could practically run a massive large language model on a smartwatch or some cheap edge device at that point.
Oh, absolutely. It completely unlocks true edge deployment for high context applications. It is arguably the most powerful new lever ML engineers have right now.
Okay, so we've basically solved the VRAM crisis for text generation because we preserve the causal mask by keeping the query separate. But what happens if we take away the need for that causal mask entirely? Like if we look at non-causal domains like computer vision, does the math change?
So it changes drastically, and it actually leads to a massive theoretical breakthrough that the authors kind of buried in the paper's appendix.
Oh, I love appendix discoveries.
Right. So when we move to vision tasks like image classification on CFAR or Tiny ImageNet or medical MRI segmentation, the sequence of image patches isn't causal. You want the model to look at the whole image at once.
It doesn't need to predict the next pixel based only on past pixels.
Exactly. In these settings, that symmetric attention matrix produced by sharing the query and the key is no longer a fatal flaw.
In fact, the ultra-constrained Q equals K equals V variant, the one that catastrophically failed in language modeling and had that 25% perplexity drop, that one actually performed the best on the Tiny ImageNet benchmark.
Yeah. Because in vision, local pixel affinity is naturally symmetric. If pixel A is part of a dog's ear next to pixel B, while pixel B is equally next to pixel A, those symmetric relationships are incredibly strong features.
Makes total sense.
Now, for synthetic tasks where order strictly matters, like sorting a sequence of numbers, symmetry is obviously still an issue. But the authors introduced this really clever workaround called the X plus variance.
How does that work?
They essentially injected a 2D positional encoding directly into the attention mechanism to artificially restore directional bias, and they did it without needing a separate projection matrix, and it completely fixed the performance drop.
That's a great engineering hack. But I really want to dig into that theoretical breakthrough in Appendix 8.1 that you mentioned, because this completely blew my mind when I read it. They asked a purely mathematical question. What happens if you take linear attention, where you replace the standard softmax operation with a positive feature map, and you apply the total Q equals K equals V collapse to it?
Yeah, this is so cool.
Can you walk us through what happens to the architecture when you do that?
Yeah, it is basically a beautiful mathematical bridge. Standard attention operates via discrete selective retrieval. The model builds a giant n-by-n attention map to look at specific pass tokens.
Right.
But if you take linear attention and you force the query, key, and value to be the exact same vector, you mathematically eliminate the token-to-token interaction matrices entirely. You just don't build an attention map at all.
Wait, if there is no attention map, what is the model actually calculating? How does it even know what to output?
It transforms into a purely recurrent formulation. The attention state evolves via outer product updates. Instead of looking backward at every previous token, the model just maintains a single running hidden state.
Oh, wow.
Yeah, every new token that comes in just updates that state and reads from it simultaneously. Conceptually and mathematically, linear attention under the Q equals K equals V constraint behaves exactly like a discrete time state space model, but with an adaptive, content-dependent observation matrix.
Hold on. Are you telling me that a transformer is basically just a state space model with a bloated projection layer? Like if we just squish Q, K, and V together in a linear transformer, we accidentally derive the exact same math underlying modern SSMs, like Mamba.
That is exactly what they proved.
That's insane.
By removing the explicit content-based routing, so that by dropping the separate Q, K, and V matrices, you shift the attention mechanism entirely away from discrete retrieval. You turn it into continuous temporal integration. It proves that transformers and state space models are not two entirely distinct species of neural networks. They exist on a mathematical continuum, and projection sharing is literally the slider that moves you between them. It is the representational structure of the model, not just its scale or its name, that determines its fundamental behavior.
That is just incredible. I mean, it proves that we have been building these massive, multi-billion parameter structures for almost a decade without fully understanding the foundational geometry underneath them.
It really forces you to take a hard look at the standard practices in deep learning, you know? How many of the architectural components we take for granted are just historical artifacts, things we built to appease the hardware or the initial frameworks of 2017, rather than actual mathematical necessities?
Which I think brings us right back down to earth for the practical takeaways for you listening right now. Q minus K equals V is a drop-in architectural tweak. It requires no special initialization. It stacks multiplicatively with whatever GQA or MQA setup you're already using, and it instantly halves your KV cache footprint during autoregressive inference.
Exactly.
I mean, if you have ever watched your GPU throw an out-of-memory error trying to serve a long context window, this is a paper you need to implement immediately.
And because it maintains downstream task accuracy, I mean, they tested it on benchmarks like HeliSwag, PIQA, and RC, and it only lost about 0.4% average accuracy against the unconstrained baseline. There's virtually no reason not to adopt this for production-serving environments.
Yeah, it's no-brainer. Which leaves us with a final provocative thought to chew on. We started by looking at the QKV structure, like an office filing system, with a search term, a folder label, and a document. And we just proved that treating the label and the document as two separate things was basically a historical accident.
Right, just a redundant waste of theorem.
A waste that the industry blindly accepted as gospel for years. So my question is, what other standard transformer components are just vestigial parameters taking up space on your GPU? Like, if we do not need 3 projections for attention, do we actually need massive MLPs in every single layer of the network?
Oh, that is exactly the kind of structural assumption the research community is going to start tearing down next.
Totally agree. Well, thank you for joining us for this deep dive into the sources on AI paper slop. We'll catch you next time. And in the meantime, keep questioning your architectural assumptions.